Hello, good evening, everyone.
Good evening, sir.
Good evening, sir.
So this is week 4 session, week 4 open session, and I hope you have completed the week 3 and you have started watching the week 4 lectures. So, any specific doubt in week 4? If you have, you can mention initially. Then we will cover in the today's session. No doubt means you haven't watched the lectures. Okay, so if there is no query from your side, then we will discuss the content of week 4, and you can ask your doubt during the session when we will discover the topics. Okay, so let's start. If you have any query, you can ask. You can open your mic in between, and you can ask. Okay, so let me share my screen. Okay, I hope my screen is visible.
Yes, sir.
Huh? Uh, Already, it is already live streamed. Sri Goka Rapu. Yeah, this is already live streamed, and live streamed is already started. I hope you can see the things on the. Let me share the copy also in the chat. Okay, okay. So fine. Week 4, as you have already seen the content in your dashboard. So week 4 is now we have started the another data structure, that very common data structure graph. Okay. So till now you have learned the sorting algorithm, searching algorithms, basic data structure like stack, queue, linked list, or basic list regarding the array things. So these are the basic structure, but some advanced data structure we have. So that we are starting from the week 4, and this data structure will also cover in the week 5. So means week 4 and week 5 are basically for the graph data structure. Okay, so here we will understand the basic graphs as well as the standard algorithms which are useful with the graph to perform some any specific task. Okay, and these algorithms are very important to perform very many real life tasks. Okay, so we will cover the things. So first in week 4 we are starting from the basics, so we will understand the graph structures, how to represent the graphs, and after that we will understand some basic algorithm, traversal algorithms, and at the last we will understand some topological sort algorithm. We will discuss what is the use case of topological sort. So regarding the content in your course page, you can see, so first lecture professor is covering introduction to graphs, second is representing graph. Okay, so both are the basic things you should know if you are entering into the graph algorithms. Okay, so these are the very basics. And after that, in the next two lecture we are learning this breadth first search and depth first search. These are the traversal algorithms. Okay, so how we traverse the graph, how we traverse each node in the graph. So we have these two algorithms, and after that we will see application of BFS and DFS, means where in the real life where we can use this BFS and DFS traversal algorithms. And at the last we have this introduction to directed acyclic graph. In short we call this as a DAG. Okay, and based on this there we have these two algorithms, topological sort and longest path in DAG. So this is also one uh, type of algorithms which solve many like dependency based problems. Okay, so let's start with the basics, so that you have already seen these contents, basic contents, in your previous course, I think CT or in math. So that is this is a similar type of things, but here we are also implementing the algorithms, we are solving the problems. I'm not sure what level of things you have already covered in the foundation level for these topics, but some idea you already have from the foundation level. Okay, so now first thing is introduction to of the graph. So I am just covering from this our GitHub notes. Okay, so that actually follows the content of the lectures, and same implementation generally we used mostly, which is covered in the lecture also. Okay, so now introduction of graph. So what is the graph actually? So it is in the definition terms, it is a non-linear data structure. Okay, so till now array we have seen and stack queue, these comes under the linear data structure. Okay, but here this is comes under the category of non-linear data structure. A graph G consists of a non-empty set B where members are called the vertices of graph, and the edge E are member of, sorry, where the set E where member are called the edge. So these are the two set basically. So this is the like say representation of the graph. So we represent by the G equal to set of V and set of E, where the V is the set of vertices in the graph and E is the set of edges in the graph. Okay, so now this is the example. So you can see, let's simulate. Okay, so this is the one example here is giving. So what is the set of V here? So any representation which is combined of the set of vertices and set of edges. So we can represent like this. So V equal to here set is uh, vertices. Okay, so that is A comma B comma C comma D comma E. Okay, so this is the set of vertices and E is the set of edges. Okay, so here some representation name is given on the each edge, so we can also write like this. So E1, E2, E3, okay, E4, E5. So this is the edges we have. Total number of edges we have 5. So we have represented like this. Otherwise, some other representation you will see later. So that is the combination of vertex. Okay, so here there is no direction on the edges. Okay, so this is called as an undirected graph. So here we can also represent it as like here A comma B inside the bracket. Okay, round bracket. So this is represent one edge A which is connected A to B. Okay, so we can read like from any side, so A to B or B to A, because there is no direction. Okay, so this is representing one s. So if we have representing this one s as like one times AB, so no need to represent another from the another side like BA. Okay, so one s can be should be represented by only one notation in here. So like B C, okay, like this we can represent all the edges in this way also. Okay, so this is the formal definition of this graph, where we represent the graph like this theoretically. Now comes to the next part. So you can see this is the representation we have already mentioned here also. So basic terminology you should know about the graph. So what is these terminology we used with the graph? So vertex or node. So this is the main unit of the graph. Okay, in a simple graph, each vertex can be connected to other vertices by edge. Vertices are often represented by circle or a dot in visual representation of graph. Okay, so the whatever we are representing inside the circle to represent the graph, that is generally called as a vertex or node. Okay, edge, this is the line between which is connecting two vertices. Okay, uh, in a graph, so that is called as a edge. This can be directed or undirected. So directed and undirected we will see later. In this week we are only covering the undirected graph. So that directed graph we will see in the next week. So where the some use cases are there. And
Sir, we are covering directed as well. If you see the
oh, we are
implementation videos in DFS,
okay, yeah, last in the last actually diagraph
in the
there
middle
also,
only,
yeah, we have.
in the
Okay,
middle
okay.
only, if you see the implementation of BFS and DFS, sir actually moved to
Oh,
traversal at the
okay,
time of
okay.
traversal. He uses this notion.
Okay,
Then
I
we
got it. So I think we are not covering the weighted graph then this week.
weighted graph is not covering. That's right.
Yes, yes. So I forgot that. So we are covering only unweighted graph, and weighted graph we will see in the next week. So that is the thing. Okay. So edge, I already mentioned, this is the connecting line between two vertices, and sometimes so this is undirected. This is maybe directed also. Sometimes you will see this is weighted or sometimes unweighted. So these are the some category when we create a graph with these type of different cases. Okay, so then we said the type of the graph is different. If we are just taking the weighted on the S, so we called that graph as a weighted graph. If we are not taking any weight on the S, so this is unweighted graph like this. So now next is degree. So degree of vertices is the number of edges that are connected to it. Okay. So if we talk about the like simple vertex, okay, suppose we have vertex A. Okay. Now here, how many other vertex are connected to this? Suppose this is like V1 and V2 and V3. Okay. Three vertex are covered onto this. So what is the degree of A is in this graph? So this is undirected graph. There is no direction in this. So we generally use the terms or degree only for this. Okay, for the undirected graph. So this is the total number of edge connected to onto this vertex. That is called the degree of this vertex. Okay. So what is the degree of V1? Only one. Okay. So what is the degree of V2? One. What is the degree of V3? One. And what is the degree of A? Three. So this is the concept of degree, and we use this term. So some questions may be theoretically asked in the exam also related to this degree. So you should know what is the degree in the undirected graph. Now next, for the directed graph, let me also tell you so that in the directed graph, so we have the direction actually. Okay, so like some edge is outgoing, some edge is in like as an incoming edge. Okay, so this is suppose v1, v2, and this is v3. So here in the directed graph we have the concept of in degree and out degree. Okay, so in degree means how many edges are coming onto this. So that is the in degree. Outgoing out degree is how many edges are going outside of this vertex. So that is called as a out degree. Total degree is the combined of in degree plus out degree. So this is the way to calculate the degree in directed graph. So here, what is the in degree of A? That is actually 1. What is the out degree of this A? That is 2. Okay, and total degree of this vertex A is 3. Like at the in degree plus out degree.
Sir,
So in this way,
what is 1 and 2 here?
so 1 is in degree and this is out degree. In degree means how many edges are coming into this A from another vertex. So that is only one edge is coming, and out degree is how many edges are going outside of this. So that is 2.
Okay, sir.
Okay, yeah. So let's move to the next. So path. So path is a sequence of vertices connected by a edge. A simple path is a path where no vertex is repeated. So simple like if we have some graph and we can say this is A is the first vertex and this is connected to B, then this is connected to C, this is connected to D, like this. Okay. So we can say that this is the path from A to D. Okay, so this A to B and B to C and C to D, this is the complete path. Okay, and simple path where there is no vertex repeated. So suppose if any cycle like this is also connected to like this, so we can also write path like A, B, C, then D, and then again C. Okay, like this. So in this path, these vertices are repeated. So this is not called as a simple path. So we are calling this is path, simple path, only if there is no vertex repeated in the path. Okay. So this path can be represented
Sir,
like this.
path.
So in the combination of
Hello.
yes.
Sir, is path is only available in directed graph or undirected graph also?
No, undirected also,
Okay.
Okay. Yeah, so this is just like a set of edges which are coming in the path. Suppose this is E1, E2, E3. So this is like a E1, E2, E3. We can consider as this is the path edge, or you can also represent like as a but with the help of vertex. So like this is A, B, C, D. So this is also
Okay.
representing as a path. Okay.
So
And
in the start of the discussion, you mentioned about linear and non-linear. So is this the reason because of you can have different paths connecting two different vertices? So is it the
yes, so
reason why
that
we are saying it's non-linear?
yes. So here there is a multiple path. Maybe you will get to like traverse. Okay. So suppose if you are starting from A to B, from here, like one path is going to this side and another path is going to this side. So this is the possibility for the multiple paths you have to traverse
Correct.
to reach it all. But so because of that, this is like a non-linear. But
Non-linear.
linear, they are the one path traverse you can visit all the things. Okay,
Right.
so that is the things for linear and non-linear.
Yeah.
Okay, so cycle is the next thing for the path. So a cycle is a path that start and ends at the same vertex. So this is any vertex. Like suppose if you are moving from A to B and then B to C and then C to A again. Okay, so here like A, then B, then C, and then again A. So here starting vertex is this and the same end vertex is also this. So this is called as a cycle in the graph. Okay, this may be in the directed also, undirected also. So directed cycle, you have to see the direction. So we cannot say like this. So this is B and suppose this is C and this is like, this is not a cycle. Okay, so here because direction we have to check. In this path we have to check the direction. So because A to B we can move, but B to C we cannot see that this is a this way we cannot move. So we can only move as per the direction. Undirected part, there is no direction, we can move in any side. So that because of that we can consider that as a cycle. So simple, this graph is given like, okay, so this is a cycle. So this is the cycle definition. And okay, so connectedness. Okay, so connectedness, a graph is said to be connected if there is a path between any two vertices in the graph. Okay, a disconnected graph is a graph that is not connected, meaning it can be broken into two or more separate components. So like if you have graph like this, so suppose this is the one part B and C and like D, E. Okay, so here this is connected like this. Okay, so suppose you can connect more also, so like this. So this complete graph we will say connected because here we can we have a path from any vertex to any another vertex. Okay, so we have the path. So this is the one component we will say this is a one connected component. Okay, in this graph. So this is called as a connected. But suppose if we have like this A to B and C, this is the one part, and D, E, and F. Okay, so we are saying that this is a one graph, but this is not connected graph. Okay, here two components are there, two connected components are there. So this is the first connected component, we can say C1, and this is the another connected component C2. Okay, but the combined graph is not connected, we will say, because we cannot we don't have any path from A to F, A to E, or like D to B in way, but one component is connected. Okay, so this is called as a connectedness. And component definition I have already sent. A component is a connected subgraph of a larger graph. So one part of the graph which is connected is called as a one component of that graph. Okay, it is a part of the graph that is connected to other vertices or edge within that part, but not connected to the rest of the graph. So this is the meaning of connectedness and component in the graph. Okay, so next thing is directed graph. So directed graph, we have already mentioned that where the edge directions are given. Okay, one arrow is given on the direct edges, so that is called as a directed graph. Undirected graph, where there is no arrow mentioned in the edges, so there is no direction given on the edges, so that is called as an undirected graph. Weighted graph, where some value or weight are assigned on the edge. Okay, so like suppose if you want to represent a your city map, okay, or your like city map of, or like station map, or like airport map, where some like that weights are there. We want to represent like city A, like this is the city A, and this is B, this is C, and this is D. These are the four cities, and we want to represent the map between these city by the connecting roads. Okay, like this. So, and we want to represent the connected road distance actually. So, how far actually A is from B. So, that distance will be considered as a one weight or value on this edge. Like this is 26, this is 50, this is like 40 and 70, like this. Okay. So, we can represent like this type of graph where these vertex are representing cities and these edges are representing connected roads, and these weights are representing the distance in kilometer or in any way. So that is just like called as a weighted graph. Okay. So these example you will see in the next week when we will discuss the shortest path algorithm, spanning tree algorithms. And next is adjacent vertices. Okay, so weighted graph is done. Adjacent vertices. Two vertices are adjacent if they are connected via an edge. Okay, so if we will see like
Sir, these weights have any use in the graph?
so this ways you will see. Suppose if you want to calculate the shortest path from one city to another city, there are multiple possible path. Okay, so
Okay.
what is the term? What things we are calculating the shortest means here? So we are just looking at what is the shortest distance between one city to another city.
Oh,
So we have to take some value or distance or some weight on the edges.
okay.
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 So weighted graph will be covered in the week 5. So some use case you will see where the spanning tree and shortest path algorithms are there. So you will see.
Okay, sir.
So here, this is like one graph and adjacent vertices we are looking. So suppose what are the adjacent vertices of A? This is very important things because this adjacent things will be used in every actually algorithms. Okay, so what are the adjacent vertices of any vertex? So adjacent vertex are the vertex which are directly connected to from that vertex. Suppose we are looking what are the adjacent of A. So the adjacent of A which are directly connected via one edge to this. So that here the adjacent vertex of A are B and D. This C is not a adjacent vertex of A because this is not directly connected to the A. Okay, so in this way we will see in our each algorithm, when you will see the BFS algorithm, DFS algorithm, we always looks the adjacent vertex to visit. So you should know how we can check the adjacent vertex. Okay, how we can get this information in the graph. So this is the meaning of adjacent actually.
Sir,
Okay, which are
similarly,
directly
adjacent vertex of B is C, na sir?
adjacent of vertex of B is C and A both.
Achha, oh, A
If
and
they
A.
are on same level, right? If we see
Huh.
just the tree structure, let's say, then if they are on same level, then they are adjacent, or maybe one level below that.
Yeah, if you are representing into the tree manner, so we cannot represent every graph in the tree initially like this. Okay, first thing, suppose if here this is also connected, is also connected, then how you will represent where from you start like this. But yeah, traversal algorithm generate the tree. Okay, traversal tree, because when
That's what confusing
if
part.
we visit any vertices, we will not visit again. So yeah, that we will discuss in the details when algorithm or the traversal algorithm. First thing is if we are looking the adjacent of any vertex, so only check what are the direct connected vertices from that vertex. So those are called as a adjacent vertex. Okay, in directed graph, so like suppose if this is A, if it is connected to B, okay, if any graph is connected to like this C this way. So what are the adjacent of A here is, so we will only see the outgoing edge.
B.
So where from we can go directly from A, okay, so that we can only move to B, which is connected directly by one edge. So this is the adjacent vertex. So this is the definition. Incidence. A vertex is incident on an edge if the vertex is one of the endpoints on the edge. So this term is used in the terms of edge actually. Suppose we have edge E1. So this edge is incident on which vertex? So that is called as a incidence. So V1, V2. Okay, suppose we want to represent the incident of E. So this E1 is connected to which vertex? So that vertices are called as a incident of this edge. Okay, so this E is connected onto V1 and V2.
Sir,
So
could you
this is
repeat
just like
once
a
again, sir?
definition from the so this incidence is term used in the reference of edges actually. Okay, so here we are looking from the edge side. So what are the vertex incident on this edge? So the vertex which are connecting on any one of the endpoint. So that is called as that vertex are incident.
So incidents always occurs in
Okay.
pairs, you are saying, sir.
So that this we can say that V2 is the one incident of this on this edge E1. Same V1 is also. So that means what vertex are? Huh? Yes,
What
someone
if,
is
sir,
speaking.
it's a directed graph?
So that is another way to say this. So like if we have the directed graph, okay, so like V1 and V2. So that EH we have. Here we will say the same things like E1 is incident from to V2. Like E1 is incident from V1 to V2. This is the statement we will say. Okay, but for the undirected graph, we can say that E1 is incident on V1 and V2.
Okay, sir.
Okay. Yeah. So this is also used to represent the graph in the incidence matrix. So let me see that will come in this content or not. So okay, delete this and move to next. Okay, now subgraph incidence is covered subgraph. So subgraph is a one subset of the graph, another graph. Okay, so one graph is given complete graph. If we take one part of the graph, that is called as a subgraph. Complete graph, yeah, this is very important term. So complete graph, a complete graph is a graph where every vertex is connected to every other vertex. So like if you have one graph, so A, B, C, D, okay, these four vertex are there. If you make the graph where every pair of this graph are connected via one edge, okay, direct edge. So like A is connected to all three remaining vertex. Okay, now B is also connected to all three remaining vertex. C is also connected, D is also connected in this way. Now you can see in this graph, each pair of vertex are connected via one direct edge. So this is called as a complete graph.
Sir,
Okay.
what is the difference between connectedness and complete graph, sir? Like, is there any correlation between them?
No, actually connectedness is just representing a graph of, so graph all the vertices are connected to. So this is also called like as A, B and C and D. Okay, this is also a connected graph. Okay, here connected graph definition is represented like where we have a path from every vertex to another vertex path. Okay, in complete graph we have the direct edge between every pair. Okay, so this is a connected graph, but this is not a complete graph.
Sir, we cannot make the complete graph on directed edge, na, sir?
We can make directed edge, you can also make the complete graph. So that directed edge, like every edge, single edge. So like this is just like I'm taking two vertex. So directed edge means one from this and another from this, like this.
Oh, sure, okay,
Complete.
two-way. Okay, got it.
Two edges will be there if directed graph is there. Okay, so this is the connected graph where we have the path from each pair of the vertex, but here complete graph means we have the direct edge between every pair. So this is the difference. And the now question comes regarding this complete graph is the very common important question. Here, if suppose if some number of vertices are given, suppose n is given like 4. Okay, so this n is representing number of vertices in the graph. So what are the maximum number of edge possible in the complete graph? Okay, so this is the very common question you will see. Okay, so this we have the direct formula for this. So here you can see this is the 4 vertex graph, and how many edge are there?
6.
6. Okay. So we have so this, suppose this question is asked like n equal to 10, then how many edge will be there? So this is now very complicated. You have to, if you created all the vertices, 10 vertices, and you are connecting all the vertices and then counting that. So for this we have the direct formula that you can use, that is n into n minus 1 divided by 2. Okay. So here just put the value of 4, and 4 into 4 minus 1, 3, and divided by 2. So that is 6. You can directly calculate this information.
So what is this formula basically? N into n minus 1 by 2?
This is representing the number of edges in the complete graph with 4 vertices. Okay, n vertices. So means, let me take another example. If it is given like that.
Sir, this is for undirected, right? For directed, we will
Undirected,
divide by 2.
Yeah.
Right.
So undirected graph. So if n is given like 10, so this information, suppose it is given like, okay, so a total number of vertices we have 10. How many maximum edge are possible in that graph? This is the question. Okay. So maximum edge means we should have the complete graph to get maximum number of edge in this information. Okay. So means with 10 vertex, what are the maximum number of edge possible in the graph? So only the complete graph contains the maximum number of edge. So we can directly calculate it, number of E equal to
45.
N equal to 10. So 10 into 9 divided by 2. So that is 45. So if you make the complete graph for this 10 vertices, you will get a total number of edges 45. Okay.
Sir, what is
So
minimum?
now this is minimum. Okay.
N minus 1, right, sir?
Okay, here this is also a very important thing. So what information is given regarding the question? So if it is mentioned that graph is connected, then this value will be different. Otherwise, if graph is maybe not connected, so this may be 0 also. Okay.
Sir, can you
So
please
suppose
repeat?
suppose if it is given that if graph has n equal to like 4 vertices, okay, what is the minimum number of edge possible for this? But it is not given here that this graph is connected or not connected. Okay, so there are two possibility here. If graph is connected with this, so minimum number of edges is possible 3. Okay, if graph is not connected, so then 0 is also possible.
Sir,
Okay, so
if you don't mind,
3 is possible, like V1, 1 second, V2, V3. Okay, if graph is connected, then I am making. Okay, so this is V4. So this is the minimum number of possibility if graph is connected with 4 vertices. Okay, so 3 edge you can see. But if graph is not connected, so this is also one possible graph for this. Okay, where each vertex are disconnected. So here 0 edge. So for minimum, so just see the question statement if connected and disconnected is given or not in the question. If this type of question will be asked, definitely something will be given regarding the graph.
Sir, to be complete, first we have to meet the condition of connected, right? Because without connected, you cannot
Complete is definitely a connected.
So minimum condition is connected, and then if the question is asked about what is the maximum for the completion, n into n minus 1 by 2. Whereas
Yes.
minimum completion is n minus 1.
N minus 1 in the connected graph. Okay, so this is regarding the undirected. Okay, undirected, but directed, because each pair in the directed graph have 2 edge now. Okay, now one is like this and another is opposite. So each edge can be represented by 2. So in the that complete graph, so just you have more multiply by 2 edge, number of edge. Okay, so if you want to make any like complete graph, directed graph. Okay, so suppose if we have 4. So A, B, C, and D. So now each pair will be connected by two edge like this. Okay. And same from here like this. So like okay. So here formula will become changed. So n into n minus 1 divided by 2. It was the formula for undirected graph, but here every edge is represented by two pair. Okay, so two edges. Every pair is represented by two pair of the edges. So just multiply 2. So this will become n into n minus 1. So if question is asked like n equal to 10 and this is a directed graph, and how many edge are possible in that maximum edge. So here the formula is n into n minus 1. Okay, so simply calculate 10 into 990. Okay, so this is the formula you can remember. This will be
Will be
very
9.
helpful to solve some problem.
Sir, minimum will be
Huh?
9, right?
Minimum will be 9 in the connected graph, but on same things disconnected maybe 0. Okay. So just make sure that this formula is very important. This question may be asked on the different side also. Suppose edge are given, then what is the minimum number of vertices possible? What is the maximum number of vertices possible in the connected graph like this? Okay. So both sides this question may be asked.
Yes, sir.
Sir, let us say n equal to 4, sir. The same as what you have shown A, B, C, D,
Huh.
right? N equal to 4, and it's a directed graph. That means
Huh.
the minimum vertices, not vertices, the minimum edges will be 2 to 4, 6, right?
No, minimum will be uh,
6, right? Because
minimum will
there
be
are
not 6.
2, 2, 4, 5, 6.
No, minimum will be
I'm not
3
talking
in the
about
connected
complete. I'm
graph.
talking about connected.
Connected, na? Still
Connected.
3.
If it is directed, then it's a double 2n minus 1, right? Sorry.
No, it is still you can make na simple with 3 edge. You can also make like A. You can make like this B. You can
Right,
make
sir.
like C. So
That is
and like D.
okay. But
So this is also called as a connected, na? Not this is not completely
okay.
disconnected.
No, it's a direct. It's a. This is a okay, directional.
This is a directional thing. So here,
Directional. If it is,
uh,
if you do a double direction, that is back, then it will be 6.
hmm,
That's what I was trying to understand.
ha. In that way, yeah. If you want to get the path between every vertices, then it will come 6.
Okay.
Sir, it would be difficult to find out the minimum number of edges for like directed graphs, right?
Ha.
Like it's not a valid formula. Like for undirected graph, we can just say minimum could be n minus 1 for a complete graph. But for a directed graph, like we should do this mathematically, like drawing each and every edge. Is there any way?
No. So if we are looking that any graph is disconnected, so in n minus 1 you will get a connected part. Okay, all are the connected. Okay. So n minus 1 you will get the same. But if you are looking the path also for between every pair, so then you have to take the like n minus 1 multiply 2 like this.
Okay, sir.
Okay, like if you want to get the path between every pair, then you have to make. So here A2 C is also path, C2 A is also path. Okay, in this way.
Yes,
So
sir. Understood.
this is the important formula. Okay, so just remember this. So sometimes the question is also asked like this: if suppose in the connected graph edge are like 25, okay, edge are 25. So what are the minimum number of vertices are possible for this, and what is the maximum number of edges possible for this? Sorry, vertex possible this. Okay, so what is the maximum vertex, and what are the minimum vertex? If this is the number of edges. Okay. So what will be the answer for the connected graph? And undirected, I'm just talking. Tell me. So what are the maximum vertex possible for this 25? The number of edges are 25.
Sir, we should. Is it an undirected graph or directed graph, sir?
Undirected and connected. Anyone? Okay, so maximum is
We can
possible when
So it's a quadratic. So it's a
Yes, sir. We'll get a quadratic.
quadratic equation, right? So we may have two values.
One of
no,
them
this
would
is
be
just like a
imaginary or
reverse
not
this.
possible, sir.
Yeah.
No. Actually, for this information, you can directly think in the reverse. So for the maximum number of vertices possibility and minimum number of vertices possibility. So maximum is possible means this value should be the minimum for any number of vertex. So 25, this is the minimum value, minimum number of edge for what number of vertices. So that is only 26. You have already seen that n minus 1 edges are required for n vertex. That is the minimum.
Sir, can you please
This is just
show
like a reverse.
Okay,
can
sir.
you please show the example with the few edges?
So here I am saying we have seen that if you are taking n number of vertices, okay, how many minimum number of edge are possible? Okay, so how many minimum number of edge are possible?
If graph is connected
This is
n
the
minus
vertex.
1.
Minimum is like we only need to
N
have n minus 1 because we have to only connect with each node only once.
Yes. Okay, we are talking about the connected and directed graph. So this is the for minimum number of for vertex n, minimum number of edge are possible this. Okay, so if we can just reverse this statement, so we have now this is the number of edge. What are the maximum number of vertex possible for this for the connected graph? So this is just like a reverse things. If n is given, means add 1 here. So this is the maximum possibility. So means suppose I am taking the example for 4. Okay, so this is the n value. And means for 4 vertex, you can make like this. So A and B and C and D. Okay, all are now connected. So 3 edge are required. So n minus 1. Okay, now information is given. 3 edge are there. Okay, so what are the maximum number of vertex possible for this? So that is
So
just like n
is it
plus 1.
giving a minimum edges or maximum edges?
No, I am just giving the edge number of edges and asking the
Yes.
what are the maximum number of vertices possible, which are connected these number of edges.
n into n minus 1 by 2.
No, not this.
Yeah, same formula I also thought. Okay, n into n minus 1.
No, that is a reverse question. This time I am giving the information of number of edges. Okay, number of edges e value I am giving. Okay, and I am asking the maximum number of vertex and minimum number of vertex. Okay, just
but,
take this as a complete graph.
Are we talking about undirected graph? Because if this is
Undirected and
graph,
connected.
then, it will always be n by n minus 1 by 2.
I'm talking about the undirected connected graph. So see here. Here this is the number of edge are 6. Okay. And what are the minimum number of vertices possible for this 6 edges is you can see here. 4. Okay.
Yes, sir.
And what are the maximum number of edge possible vertex possible for the same 6 edges? If you connect each edge by 2 different pair, like so this A, B, C, okay, and D, E, F, like this, 1, 2, 3, 4, 5, 6, okay, G. Okay, so this is also one possible graph. Okay, this is also one possible graph with the same 6 number of vertices, but this time number of vertices are more. That is the maximum possible that is 6 plus 1 equal to 7. So this is the
Okay.
max. Okay,
Got
and
it.
this is the min. So this is the reverse question from the same which we have seen before. If vertex is given,
How
then
you
what is the minimum and maximum?
how you computed this min?
Min, this min.
Hmm.
So this you can calculate it like how we calculated the E. N into n minus 1 divided by 2.
But here we have edges, right? 6 edges. So 6 is
Huh.
6. So there
So
will be an
here you
equation
have,
form.
so, yeah, that is the equation. But for the question solving, you can put a value n and see you are getting more than this and like less value.
Sir,
Suppose
say,
if you have the 6,
mhm.
if you have the 6 number of edges, okay, so you can take some random value for the n initially, like 3. Okay, suppose you are taking 3.
Hmm.
So just apply the same formula, 3 into 3 2 divided by 2. Okay, so you are getting 3. So this is the means for if you are taking n equal to 3.
Hmm.
So only maximum edge are possible 3. So this cannot be the answer. Okay, then we will increase this value. So at first value, when you will get a more number of edges,
Hmm.
that will be the answer.
Sir, if you say like this, then say 100, okay? Now, if I
Huh.
have 100 edges, then if I go by this way, like substituting values, it won't be a easy task, right? So, is there some way so that I can get around some ballpark figure, like getting a square or something like that?
That will also be, you will get a like fractional value, point decimal value, some things. Okay, so in that way, because here graph is possible with any value of the edges. Okay, so but also the number of vertex will also be always a integer value, not the fractional value.
Okay.
Correct. So that we can use this formula. So you can randomly put like value, like you can put here 10. Okay, and you can get this which side you should go. Okay, so like 10 into 9 divided by 2, you are getting like sorry,
45.
this 45 you are getting. Directly increase to 12 means this value will be, you will get 11 and divided by 2. Okay, 6. This time is also you are getting. So you can directly
So,
put
my aim
15 or
should be,
something.
sir, so my
Huh.
aim should be either 100 or less than something very close to 100, right?
No, either 100 or greater 100. Then only possible.
Okay.
Greater is the closest greater,
Okay, yes, we are
not
fine.
the more greater. Okay, suppose if this is 14, let me try this. So 7, so 15 7 ja 7 and 735, so
105.
105 na.
Hmm.
So we are getting, you can see we are getting 105. So check for one less value for also. So like 14 into 13 divided by 2. So this is
What
so
are
you
you
calculate
solving?
Thank you.
so we are just looking for what are the minimum number of vertex required for these number of edges.
Sir, to
The
find the minimum number of vertices, we need to use the n into n minus 1 divided by 2 formula, no?
No, that was the minimum number of
Sir, yes,
edges. This
yes.
is the reverse thing. This is
This
the
is
reverse question.
vertices. You are finding minimum number of vertices here.
How minimum number of vertex we are looking. So here you can see 13 7 ja 91.
91.
So now you are getting less. So you have the 100 edge in the graph. So this 14 vertex are not possible because for 14 vertex maximum number of
Understood.
edge are 91.
Mhm.
So you cannot take this, but 15 you can take. For 15 you are getting maximum number of these 105 edge, but graph have this number. So this is also possible with 15.
Got it.
Okay, because we are looking for the minimum number of vertex for 100. So that is only 15 answer possible. So this is also possible for 16 17, but we are looking for the minimum number. So this is the minimum possible answer for this. So in this way you can calculate the reverse question also. So this generally question not ask for the very big value or something. So you will get only
Sir,
some value that you can easily recognize.
sir, if you don't mind, sir, if I ask you how you get 13 by 2, can you tell me, please?
So we use the same formula. Na? Let me again quickly discuss. So information is given like suppose if information is given like 120 edges are there. Okay, we have a graph where the number of edges are 120. Now we are looking for the minimum number of vertex for this number of edges. So graph with minimum number of vertex can contain these number of edges. This is the information we are looking for. Okay, so
Okay.
we know that we can directly calculate the what is the maximum number of edge possible if n then number of vertex are given. So we can try with some initial value. We can just start with any random value, like you can start with 12. Okay,
Okay,
so
so
suppose we
okay,
are taking
we will try number on n. Well, we will give an n value
we are just
and we will check
yes,
what value is equals to or greater than 120. Okay,
equal to or closest to the more than this. Okay, not we will not take any bigger value, which
okay,
is the
okay. The
closest
closest to.
possible. Hmm.
Okay.
Okay, so we are just taking the n number of vertex randomly, and we are checking what are the maximum number of edge possible. If there's maximum number of edge crossing this value and closest, that is the answer for this.
So, sir, this is the only way to find minimum number.
So this reverse question you can solve quickly by in this way only. Otherwise, you
Okay.
have to solve some equation where you will get some fractional answer also. You can try that, but you have to take some like that floor value or ceiling value like this.
Okay, okay, got it.
Okay, so that is also a complex thing. So you have to apply the formula for that. Okay, reverse answer is possible. Like suppose if you just put the same e equal to n into n minus 1 divided by 2. So just solve this question and just take the value this 120, and now this become 240 equal to
Yes, sir.
n
This is
square
a bit
minus 1.
easier, sir. Actually, solving
Okay,
this
so if you
quadratic
can
could be easy.
yeah, if you are mathematically fine, you can solve this. Okay, so that will be good. If then take the integer value for n
Yes, sir.
and check for which value you are getting the closure answer.
Okay, sir.
Okay, so this is the basic part. Now moves to the next things. Sorry. So now this is the just logical representation of the graph. So as this is a logical representation, okay, uh, in our computer every data is stored in some memory, okay, and logically that are connected, and which we can draw that logical connection in this way. Okay, memory is just like a memory addresses, and that address are maybe in any place in the memory, and but we are linking like this, okay, by the edge. So this is the logical representation to represent the graph. So this is the undirected graph, this is the directed graph, and we have this undirected and weighted graph. Okay, some weights are given on the undirected edge. Another side is directed and weighted graph. So directions are given on the edge as well as the weight are given on the edge. Now comes to the, so this is totally theoretical things, how we represent, how what are the terms. Now comes to the how we represent these graphs, okay, and how we can also represent in our program. So because definitely when we will work with this graph information, we have to store this data in some data structure, and where we can use that data as a graph, like, okay, so in the graph terminology we can just uh, perform all the works in the graph manner. So we require some representation in the data structure. So that what are the representation we can use? So graph representation in data structure is a adjacency matrix. Okay, one is the adjacency matrix, another is a adjacency list. So adjacency matrix is just like a two-dimensional data structure we will use for this. So two-dimensional, you know that if you create a nested list, okay, list under the list, so you can use like that as a matrix form. So matrix, as per the name, this is a two-dimensional things, where the one directional is represent like rows and another is column. Okay, so this is just like a one list of list, okay, like this. You can just relate to this in your Python list. So you are maintaining list of list. So this is the one complete list, and inside that you have another 4 list like this. Okay. So each uh, inner list is just represent as a rows. Okay. So you can just give the index 0, 1, 2, 3. Okay. And each inner list, how many elements that contains, so that index is represent as a column column index. Okay. Suppose if you are storing 5, so like 0, 1, 2, 3, 4 for the each. So each inner list will contain the same number of elements that will represent the number of columns. So this is just like a matrix representation. So you can represent this matrix representation with the help of nested Python list as well as NumPy array. Okay. So NumPy array, you can also create a 2-dimensional list. So then we can store our all graph information with the help of adjacency matrix representation. Another way is adjacency list. Okay, so adjacency list is also another way. In normal structure, like if you are using any other programming language like C or C thing, so we maintain a like link list for this. So because of that, this name is given as a adjacency list. This is not like a Python list. This is a adjacency list in the terms of link list. So here, suppose if you have the 5 vertex in the graph, okay, so like 0, 1, 2, 3, 4, like this. Okay, you have 5 vertex in the graph. So for each vertex, we will create a one link list. Okay, 0, 1, 2, 3, 4. Okay, so this is just like a starting vertex, as a like a head you have seen in the link list. So this is just like a head for each, and each head is connected to their adjacent vertex. Okay, so just like a node like this. Okay, what are the adjacent of 0 that will come inside this list, link list? Okay, and at the last end. Same for what are the adjacent of 1. So suppose only one adjacent is there, so only one will we come in
Here
this
we
link.
use the two linked list, na, sir. One is for vertices and other is for who are the connected
Ha,
with this vertex.
ha, in this way you can also do. So same like you can use, so this is just like you can consider as a one link list. Okay, in this way
Yes,
also
sir.
you can represent. So I'm just representing this adjacency list representation, which is not we are using in the our course. We will not use the link list for to represent this adjacency list. Instead of this, we will use the dictionary. Okay. So because dictionary will also achieve our goal for the link list. So this is the representation actually in the adjacency list, where adjacency, as per the name you can see, adjacency list means each list contains the adjacent nodes information for each vertex. Okay, so each link list is just like a adjacent vertex information containing for each vertex. So this is the information, and same this is adjacency matrix. So here also we represent like a if 1 is connected to a 2, so corresponding cell will be considered as a 1. Okay, so this means 1 is 2, 1 or 2 is connected. If 1 and 3 is not connected, means 0. So in this way, we are filling this adjacency matrix. If we have the edge between two vertex, then 1. If we don't have the edge, then 0. So we are representing our graph in this two way, adjacency matrix and adjacency list. Yeah, so this is just a normal representation of adjacency list, but in our code, we will use the dictionary for this. So each key of the dictionary, just we will represent as a key of the dictionary, and the value is just like a list. What are the adjacent vertex of this 0? Okay, so like 1, 3, 5, like this. Okay, and then second key is the second another vertex 1. Then what are the adjacent vertex for this? Okay, so like 2, and what are the adjacent for like this 5? Okay, like this. So for each vertex we will make a key, and for as a value we will represent all the adjacent vertex of that key. Okay, so this is just like a adjacency list representation in Python. We will use the dictionary.
Sir, in the adjacency matrix, it's a fixed space, whereas adjacency list is a reduced space because
Yeah.
you're only putting what is required. Whereas in the array, sorry, in the adjacent matrix, you whether you need or not, you're putting the whole space inside. Is that my understanding?
Yes, correct. So this is the advantage of linked list.
Okay.
Okay.
Thanks.
Sir, in adjacency list, the dictionary is the vertex and the list would be outgoing vertexes. Are they
Outgoing,
okay?
outgoing,
Okay, okay,
yes.
sir. Yeah.
Hmm. So
Sir, can you
adjacent means only the connect.
sir, can you explain the adjacency matrix for directed graph? Means which row
Huh.
indicate the outgoing or ingoing row or column?
Okay, so that we will see in the example later in the next, I think. So let's see that. Okay. So I think you will get an understand. So let's see. This is the unweighted directed graph. Okay, unweighted directed graph we are looking. Okay, so here this is a directed graph. How we can represent this as a adjacency matrix and adjacency list. So here you can see this is the graph formally definition. So G equal to VE, V is the set of this, E is these S. So here each edge is just representing by a okay, so this is also one important point. If any but like graph V1, so one second. So V1 is connected to V2. So this edge can be represented either like V1 comma V2 or V2 comma V1. Both are correct. Okay, but if any as V1 is like this is a directed graph. So in the like in this definition, we will only represent like V1 comma V2. So this is the correct way to represent directed. Okay, we cannot write this V2 comma V1 this. Okay, so this is wrong for the directed edge. Okay, but undirected we can represent in the both way. Also in the our representation, unlike in our dictionary or in our matrix, we have to store the information from both sides, v1 to v2 and v2 to v1. Both place we have to put the one value. Okay, but for directed as we will only put the value for v1 to v2, not v2 to v1, like this. So let's see the example here to understand this. So this is the one graph. So each edge is just like a 0 and 1, means 0 to 1, 0 to 2. Okay, not just like a reverse, we can say this is a directed graph. So here now comes to this. So how we can represent using the adjacency matrix representation. Okay, so let's see this first. So see this. So these are the edges. Okay, E list is given as a edges. Now we are just using this code. Okay, so this code will generate this matrix. This is a numpy array matrix. Okay, so because of that, this representation is coming. So how this is just representing the edge. Okay, so I'm just making this is in the simple way. So we have total number of vertices 0 1 2 3 4. Okay, so we will make this as a 0 1 2 3
5
4.
cross 5 matrix, huh, sir?
Yes, 0 1 2 3 4. So this is just like a n by n matrix. If n, sorry, v by v matrix, we can say that. Okay, and each cross value of this row and column will represent the information of edge. If there is an edge, we will put the 1, otherwise 0. So here 0 to 1, you can say 0 to 1, one edge is there. So 0 to 1, this is the point. Okay, so we will just write a 1 here. 0 to 2, so 0 to 2, this is also one edge. So here direction we are looking from row to column side only. Okay, row to column side in the directed graph. So 1 to 3, so 1 to 3, so 1 to 3 is just like a here. So this is 1. 1 to 4, this is 1. Okay, 2 to 4, 2 to 4 is this one, and 2 to 3, 2 to 3, so this is this one, and 3 to 4. Okay, and there is no outgoing edge from 4. So this is just like a value we are filling, other all value will be 0. Okay, and this is all 0. It's like this. So this is the adjacency matrix information. You can see we are getting the same. Okay, so in this way we are representing. So in the code you can see simple what we are doing. We are creating a first 0 matrix of size by size. You can see 2D matrix we are creating. So size is representing line of V. So 5 by 5 matrix we will get, that is the 0 matrix. After that we are reading all the this tuple from this list which is representing one edge. So I comma j in E, and for each this combination we are putting 1. Okay, by default this matrix was 0 matrix, so we are just putting the 1, so all will remain 0. So we are getting this information now from this. So now this is just like a one data structure we have, and that is representing our graph information. So we have number of vertices, means number of rows and number of columns both are same, so that is representing number of vertices, and connection is representing by the inner value. Okay, so means 0 to 1 we have the edge. So if we want to suppose if we have this graph and we want to get the how many, what are the number of adjacent of 2. Okay, what number of adjacent of 2, or what are the adjacent of 2. So how you will
Three,
get from this?
three, four.
So if you are looking the adjacent of 2, just traverse this row, just traverse this row and see for which column value we are getting, we have the value 1, that is a adjacent of 2. Okay, so for 2 you can see this is 0, this is 0, this is 0, yeah, this is 1, so corresponding column is 3, so this is another vertex, so means 3 is the adjacent of 2. Same, this is again 1, so means corresponding column index is representing the vertex, so that is 4 is also adjacent of 2. So we are getting this information. Okay, 3 and 4 are the adjacent of 2. So this is the
Sir, we
very
should say
important
they're
part.
outgoing edges, right? Better than adjacent.
Outgoing edge, outgoing edge. No. Adjacent or outgoing is the same things, no?
But like we can't say that 3's adjacent is 2, right? Because this is a directed graph, there is no incoming edge from 3 for 2 from 3.
So
That's why.
in 1 second. So in a directed graph, if we have this vertex, like, so what are the adjacent of A's, B, and C? Only the outgoing edge in the directed graph are considered as the adjacent of that. Okay, so A adjacent of A is B and C, but we cannot say that the adjacent of B is A.
Okay, sir. Okay.
Okay,
Got it, sir.
so in
Yeah.
directed graph, outgoing edge is only represent that adjacent. But in directed graph, you will see this is B, this is C. So here, what are the adjacent of A, B, and C? And what are the adjacent of B? Then A also is the adjacent. Okay, because of that, in adjacency matrix, we will fill the value 1 from both sides. A to B we will fill 1, and B to A we will also fill 1. So that is the next example for this. Okay, so any query?
Sir, if a question comes that find the incoming edge and outgoing edge for the vertex 2 from the given adjacency matrix, so how
Hmm.
do that?
So what are the outgoing edge you are looking for 2? Okay, outgoing or incoming you are saying, correct?
Yes.
So for outgoing edge, traverse row. Okay, and these are the, so row to column. Actually, outgoing edge is representing row to column index. Okay, so just check from rows, just select the 2 index. So this is the vertex we are looking the outgoing edge. So that is that 3 and 4 are the outgoing edge. Okay, for incoming edge, see this column. Okay, from where you are getting the 1 value. So you are getting the 1 value from 0. Okay, now this column, there is no edges coming on this 2. So only the 0 is the incoming edge.
Okay, sir.
Okay, so in this way you can get all the information. Also, one thing, doesn't matter how many adjacents are there. Suppose this graph is very big, 100 by 100. Okay, 100 by 100, so 100 vertex are there. And suppose if any vertex you are looking like, what are the adjacent of 25 number of vertex? Okay, and suppose only the one vertex is there for this, like any 30, like this. But still you have to traverse all the 100 vertex to get this information. Okay, so suppose for the specific row like 25 row, you have to traverse each column, 100 columns, then you can identify that how many vertex you are the adjacent of this 25. So
But in
means
the
you are
previous week, we have seen that since the internal implementation of Python arrays, are like Python lists are like arrays, so each element can be accessed in constant time. But in
No, I am
NumPy,
talking.
but in
No, no,
NumPy,
no.
it is completely used as a linked list. So instead of using NumPy, if we could just use the normal Python list, will it that lead to improvement in performance?
No, I think you are confusing in the things. So this is just like a matrix representation using the NumPy. If you are representing the same adjacency matrix using the that nested Python list, you will get the same things. Okay, but the thing is, this is generated by this NumPy part. Okay, NumPy things. Same indexing you have to use like this. Okay, inside the square bracket I comma j. Same complexity, same type of functionality you have to apply here. And in Python list you have to actually create a list like this. So like in Python list you will create a like one list. Sorry. So L equal to, and inside this, like, okay, so this is just a nested list. So this is a Python list. Okay, same things where the each, this is the 0 row, this is the 1 row, this is the 2 row. Okay, this each list is just representing a row. Inside each value, like 1 5 3 2 4 6, okay, 2 4 6 5 1 2, like this. So this is just like a column, column 0 1 and 2. If you represent this in the 2D form, so this is the same 2D structure like this. Okay, like both are the same. Okay, so here this 0, this 1 is coming like second, this is 2 like this. Okay, and each like this 1 comma 5 comma 3 and 2 comma 4 comma 6 and 5 comma 1 comma 2. Okay, so these are the columns 0 1 2. Same matrix you have here. You have to suppose name is the list for L, so you have to traverse like row index 0 and column index 1. So in Python list, this is the only change. You can access the element like this. In NumPy array you have to take like this 0 comma 1. So only the difference is this, otherwise no, there is no difference in the NumPy and Python list. Okay, in the terms of traversing or accessing this information. So both are given. So I think Python version is also given in this notes. So let's see that also. So if you see, so you can see this is the Python list example. So we are implementing adjacency matrix with the help of NumPy array, two-dimensional array, or Python two nested lists. Okay, so same matrix form we are representing. So here you can see we are getting the same type of structure for this data. Okay, so this is just. Okay, so this is just like a matrix we are implementing in two different way, but the time will take similar for the both. And one important thing, so as I said that if you have the 100 by 100 matrix, means 100 vertex you are looking for. If any vertex contains any suppose one adjacent, but to get this information you have to traverse 100 times. Okay, so you have to traverse all the columns for this, then you will get a, this is the only one adjacent for this. Okay, so this is the complexity, you can say that. So what is the complexity to get this information? So here you can see total number of 5 vertex are there. Okay, 5 vertex in this example. But if you want to see what are the adjacent of 2, you have to traverse all the columns. Column is just equivalent to 5 total number of vertex. If number of vertex are b, so you have to traverse each column value in this row. So means the complexity for this operation, if you want to calculate how many vertex are there and what are the vertex adjacent vertex are of this 2, means the complexity is v.
V
Okay,
or
you have
C,
to
sir?
run a
Because
so
it could be the columns could be higher than the rows, right? Because
no,
if it's not a square
no,
matrix.
this is a square matrix.
Oh, it has to be a square matrix always.
Always.
Right.
So adjacency matrix
Sure.
is always a square
Yeah.
matrix. So means
Understood.
number of row is also representing vertex, number of column is also
Understood.
representing vertex.
Correct. You're right. So it's a
Okay,
V, O of
so
V.
complexity for this is O of V. But now comes to the So you can see this is the same loop we are running, but this time we have created a Python list. Inside that we have created another Python list as a nested list, okay, and append that. So in this way we have created the same structure. Now comes to the next, how we can implement the adjacency list in Python. So that is the important things and efficient things. So adjacency list representation. So here we can use this dictionary. Okay, this is the dictionary. Same as and set we have. Okay, and now we will create a key for each vertex. Okay, so you can see this loop. This loop you can see first loop. So this is just like linear loop, and we are initializing the key. Okay, for each I. So we have total 5 vertex, and for each I index 0, 1, 2, 3, 4. So we are creating a dictionary. So that dictionary is just like creating 0 and empty list. Okay, and 1, then empty list. So this is just like an initialization. 2, 3. Sorry, 3 and 4. So this is just like a initialization of a empty value for each key, and key is just like a each vertex. And after that, from the edge list we are looking I comma j for in this e list, and for each I we will append j. Okay, so append, we are appending in the list which we have assigned as a value, empty value. Okay, so 0 comma 1. So this is 1. Okay, so 0 comma 1 means this 0 to 1. So 1 is the adjacent of this, so 1 will be append into this list. Now 0 to 2, so then 2 will also append into this. 1 to 3, so 3 will append into this. And 1 to 4, so this 4 will also append. Now 2 to 4, so 4 will append. 2 to 3, 3 will append. Now 3 to 4, 4 will append. Okay, now all the information is stored in this dictionary. Now this time, if we want to find out the adjacent of vertex, so we will only look for the key. So a list, a list and 2. We will just get this information. This will only return the adjacent nodes, vertex 2 and 3. So 4 and 3. So this is a constant operation. In the matrix, you have to traverse each the column to get this information. But here you can, in one constant operation, you will get all the adjacent. Okay. So here, suppose if you have a 100 by 100 matrix, and suppose if any vertex is contain only one adjacent, so you can get this information in one constant time directly. So this is the advantage of adjacency list. You can get this adjacent vertex information in constant time here, but in linear time in the adjacency matrix. So this will improve the efficiency of our algorithms also. This operation. Okay. So I hope this is clear.
Yes, sir.
Yes, sir.
One more thing. So this is just like a so this is I'm talking about the directed graph only. So let's see, undirected graph is given. So that is also one important thing. So unweighted undirected graph. Okay. So here actually now each edge is one edge is given like 0 to 1, but we have to put 2 entry for this. Okay. So 0 comma 1 is one edge, but this is undirected. So in our matrix, so for this graph, undirected graph, so we have total so we have total 0 1 2 3 4. Okay, and 0 1 2 3 4. So this is again the same matrix, but this time 0 to 1. So 0 to 1 is here. Okay, now the reverse of this 1 to 0 for this edge, that entry should also be happening. So 1 to 0. Each edge will be represented by 2 entry here. Okay, so 0 to 1 and 1 to 0. So same 0 to 2, 1, and 2 to 0, 1.
Sir, how
And
are you identifying that this is a directed or undirected graph, sir?
so this is given in the top, no? So that
Okay,
is
okay.
given here. Okay.
You're
So this information is only for the undirected.
okay. Without the information of whether it is directed or undirected graph, we cannot say that single
So
edge, like,
this information will you can assume that this will always be given.
okay, sir.
Okay, this is the required information. So this 1 to 3, so 1 to 3 is just like a 1 here and 3 to 1. Okay, so this here. So each edge is representing by 2 entry in the adjacency matrix as well as the adjacency list. Okay, so like this. So 1 4 is here. No, sorry, 1 4 is here and 4 1. So 4 1 is here. See. Okay, so just fill like this. So you will get, and the remaining value you will get as a 0. So here, if you are looking the adjacent vertex, so here you will get the information from both sides, because one, what are the adjacent of 0? Suppose 0. Okay, so adjacent of 0 is 1 and 2. But if you're looking from the 1, then this 0 should also come as adjacent. Na? So because of that, we are putting this information. So here as 0 to 1 and 0 to 2. So adjacent of 0 are 1 and 2. So because of that, we are getting this here. But if you are looking from one side, so this 0 should come up. Okay, so because of that, we are also putting the another side value for this. So then we will get a 0 is the adjacent of this undirected graph. So here each edge is represented by 2 entry. So this is the things, only the change in undirected graph. And now the code you can see, if this information is given, suppose if edges are given like one edge for each representation of the edge. Okay, so one entry for each edge in given in the list. So this 0 and 1 is given only for the one edge. Okay, so sometimes you will get 1 and 0 also in the list, because if this is given in the undirected graph, so you have to, if this is not given, so you have to make this edge double. So for 0 1 you have to add 1 0 also in this list. Okay, for 0 2 2 0 you have to also add. So these things you have to done by this code, and after that we have put the same code. Okay, so for each I
Sir,
comma j combination we will put
hello.
yes.
Sir, we can remove the we can avoid this UE variable, na sir. We can directly when we are assigning one to ij position, we can also
Yes,
write
that
the
you can
line
do.
ji. We can
Yes,
also
yes, that
write
you
the
can do.
okay,
This you can do. Okay, so here you just put the e. Okay, and here just put the another variable like a met
ji.
and j comma I.
Hmm.
That is also fine. Okay.
Okay, sir.
So this is our goal here. So, and the same we will do for the adjacency list. Okay, for each edge, same things you can do. So here 0 to 1. So 0 we have the key, 1 we have the key. So 0 to 1 entry should come like this in the list. Okay, but 1 to 0 should also come in the adjacency list value. Okay, so each 0 to 1 both entries should be there. So 0 to 1 and 1 to 0 for the undirected graph. So this is like a Python list. Oh, so this is just like a nested list. This is not a adjacency list. This is the example. Okay, so here you can see in this final list. So 0 to 1 you have, then reverse you will also get. You can see 1 to 0 also have. Okay, 0 to 2 have, so 2 to 0 is also there. Okay, so each pair you will get 0 to u and v and u you will get the both entry. Okay, so this is all about the basics if you want to work with the graph. Okay, this should be very clear. So now once you will get this representation, then you can implement in the algorithms, because each algorithm requires this data as an input. Now you have to work with the that type of data, like either adjacency list or adjacency matrix. Then you should know how to get the adjacent. That is also very one important part of this algorithm operation, so that how to get the adjacent of each vertex. So I have already mentioned that how to get the adjacent in adjacency matrix and how to get the adjacent in adjacency list. So adjacency list is much better because we can directly fetch this information in constant time. But to get this information from adjacency matrix, you have to traverse each column on the adjacency matrix to get this information. So that is costly. So now this is the basic part we have covered. Now comes to the main algorithms for this week. Okay, so now these two two algorithms we have. These are the traversing algorithms. Okay, so traversing is the basic task of the graph. We want just visit each vertex which is given in the graph. Okay, so this is our target here, and both algorithms fulfill this target. Okay, means we want to traverse or visit each of the node in the graph. So how we can do this? So we have these two algorithms: breadth first search and depth first search. So as per the name, breadth first search, okay, this is used to traverse a graph or a tree. We can apply this algorithm for both graph and tree. Okay, it will work fine. And BFS start at a root or any vertex in the graph and explore all the neighbors node at the first. Okay, it will always traverse the neighbors first, then moves to the next level neighbors. So suppose I'm just explaining this with some tree structure. So to explain, so like A, this is the root vertex where we want to start. Okay, and suppose this is connect like this. Mm, okay, suppose this is just I'm just giving the name also, so this will understand. B, C, D, E, F, G, H, I, J. Okay, so suppose if we applied this BFS algorithm on the first node A, okay, and this structure we have given. So means this algorithm, how this algorithm will work. So this is the A, this is the first node should be traversed. After that, what are the adjacent of this A? That should be traversed first. So means from after traversing A, we have to traverse this B, C, D. Okay, here order may be different, but all these which are neighbor of A should be traversed first. Then next level, what are the next adjacent of? So after completing all the traversing of this adjacent level, so this is just like a one adjacent level. And what are the next adjacent levels? So we will check what are the adjacent for B. So this is E. Okay, so that should be traversed first. Okay, and what are the next adjacent of C? So C only F. So that F is there. What are the adjacent of D? That is G and H. So G and H. So like this can be traversed. So this is the way we are only discussing. We are only traversing the adjacent neighbors wise. First, we will traverse all the adjacent. Then we will move to the next level of adjacents. So this is the only way. But in this way, so if you're traversing A, then you can traverse in any order of this levels. Okay, so because all the adjacent of A are B, C, D. So no matter what order you are traversing like this. Okay, but if you writing any implementation for this, definitely implementation will work in some one specific way. Okay, not like a random things. But
Sir,
conceptually,
here you said that we have to first explore the neighbors, right? So B, C, D.
yes.
But within B,
Hmm.
you move to E, F, G, H, right? So
Huh.
means how it is traversing means like it is not, it is the next level. E is the next level, right?
So once we will traverse all these three B, C, D,
Hmm.
then we will look for the adjacent of these. Okay, B and C and E. So what are the adjacent of B? We have only E. Okay.
Hmm.
What are the adjacent of C? We have only F. Okay. What are the adjacent of D? We have this G and H.
One more
So
thing
means we will.
here, this structure actually looks like a tree, but as you said, all
Yes.
graphs can't be a tree, right? We can't have a
So
directory. So can you explain in that sense as well?
okay, so yeah, that I have explained because to explain the label things. Okay, so how this is adjacent neighbor, which I am saying that what are the adjacent
Mhm.
neighbor label actually. Okay, but in general graph may be any type of structure, but still the adjacent label wise you will get the same label things. So like suppose if graph is given like this. Okay, C, D, E, F, okay, G, H. Okay, this
Mhm.
is okay.
Okay.
Okay, this is just like graph. Okay, and let's I start with E.
Okay.
Or you can start with any vertex if you are feeling that. Okay, suppose I'm starting with B. Okay, that is looking better. So B, okay. So here, if I'm starting from B, so B is the first visited node. Okay.
Okay.
Now after that, I am looking for what are the adjacent of B.
A, E, and D, and C as well. Yes.
A, C, D, and E. All are the
Mhm.
adjacent.
Yes.
So means after visiting B, these sets should be visited. Okay. So now these should be visited.
Okay.
So in our traversal order, we can write like this. So B after B, this set of vertices should be visited. A, C, D, E. Doesn't matter. You can visit in any order conceptually, but all these vertex should be visited first.
Okay.
Then only we will check the adjacent of these vertex. A,
Now
C,
A
D,
don't
E.
have any adjacent,
So A, we have the adjacent B and C, but B is
but they
already
are visited.
traversed.
Hmm.
C, yes. So if any adjacent is already visited, so we will not visit it again. Okay. So that is the condition we will take in the algorithm. So we
Mhm.
will only visit the vertex which is not visited yet.
Okay. So
So yeah,
C
but
can
we are
have
getting
G.
this information now. So we are getting
Hmm.
this information that A have the adjacent B and C, but that is
Mhm.
already marked visited. Okay, in this till this point.
Yes, sir.
So
Okay.
B, okay. Now check for C. So C we
C
have the
has
adjacent
E.
A, B, G, but A, B is already marked, but G is the new, which is
Hmm.
not visited yet.
Hmm.
Okay, so now G will come onto this next level.
Okay, so it will not go like B, then A,
Hmm.
then exploring all the levels of A, like C, G. It is not going like DFS. Okay, understood.
No,
Hmm.
this is not like DFS.
So
This
now
will
we
only
will
traverse
add
the
G
all
there,
adjacent.
no? Sir, after that
Huh,
particular.
we have added so in order we will just added G here.
Okay.
Okay, but this is also generating like a tree. So because of that I'm generating tree, traversal tree. This is called as a
Mhm.
traversal tree.
Okay.
So now comes to the next D. Okay, what are the adjacent of D we have? So we have
F.
D, E, G, F.
F is
Okay,
not visited.
so F is only not visited. Other all are visited. So we
Hmm.
will just traverse F from here. Okay, so that is F will cover. And
So,
after that E, we
mhm.
have only B and D and F. So only I think all are visited. Okay, so nothing is
Yes.
remaining. So
Sir,
this is
here,
the
one more thing. Like we have visited G, right? And we have also visited F, but as per our graph, G can directly visit F itself.
G can directly visit it, but we can also visit it from the D. Now that okay, so D. 1 second. C is visited from
But sir,
G.
for
Okay, okay.
G, but sir, for G to visit F, we need to level three. Well, we need to go to the level three.
Exhaust
Where
D and E
Yeah.
also, right? Then
because
only
Yeah.
we can.
we
So
we are we are
as
currently on
as I
level two.
said that first we are looking the all adjacent of this B. Okay.
Hmm.
After visiting all the adjacent of this B, we will look for all the adjacent of this level.
Exhaust all the possible paths that is possible at this
Hmm.
particular
Yes.
level, right?
So
A,
first we
C,
will
D.
complete all the adjacent of this level vertex,
Mhm.
and we will traverse those vertex. So all will come
Okay.
on the next level.
Okay.
What are the
And in
possible?
DFS, we can directly visit from G to F.
So
Right.
DFS we will see. Okay, so this is the concept of BFS.
I
Okay, so
understand.
here you can see this. We are generating this type of tree structure when we are traversing. So this is called as a BFS traversal tree.
I asked this because today I was solving questions, okay, regarding these BFS, and I was not getting how they are not moving from adjacent. Like they, as I said, right? G to F we can directly visit, but they are not visiting. So I got
Yeah,
confused there. What I was doing
yeah.
was that
Without finishing the
I was
previous
not
level
visiting
vertex to
entire
check.
thing. But it said that you have to visit in alphabetical order. So
So that I
I
said
thought,
that
Mhm.
conceptually there is no order required at one level.
Hmm. Okay.
So here if I am writing this traversal order like B, A, C, D, E, G, F, this is also correct. I can also write B, C, A, D, E, G, F. This is also correct conceptually,
Hmm.
because
At a single level,
we
no
are
order.
following. No ordering is required, but our code will follow some specific order because that is written in this way.
Okay.
Okay, if you are
Oh,
writing any code, definitely that code will traverse these adjacent level in some specific order from the our data structure, so that it will only generate a one specific way. But conceptually both are correct. So this is also correct, this is also correct. Conceptually we are only looking the adjacent, we are traversing adjacent level by neighbors wise or not. This is we are only looking, but code will generate only one specific way. So in these questions you will also get this information in the questions, like suppose if we are looking for the one specific answer for the question, so some information will be given, like if you have more than one adjacent level, traverse alphabetically. Okay, so in that way you will only get a one specific order. So after B, only in the next adjacent level you have to traverse in the alphabetical way, so that B, sorry, A, C, D, E, this is the only order will come in the with this given information. After that you will traverse this A adjacent first. So what are the adjacent of A is G, G will come, and then C, what are the adjacent of C? Sorry, there's nothing from A, but C is G, but D is F. So this order only will come as a one answer. If the question
understood, sir.
is mentioned that traverse alphabetically like this. So this is the concept of BFS and how we maintain this information. That we have done this. How we actually uh, get this through the code means how we will complete all the neighbors first, then we will move to next level. So we use the queue data structure for this. Okay, so BFS use queue data structure for this. So how queue used? So let's remove this part. So how we can get this through the queue? Okay, so we will just maintain one queue. Okay, you know the concept of queue, last in first out. This is correct? No, first in
Sir,
first out.
first in, first out.
First in, first
Huh.
out, sir.
First in first out. Okay, so what we will do for this, suppose if how we can achieve this. So if we start from the B, this is the starting vertex. So what we will do, we will just do the same process when we are just taking one any vertex. So we will enter that vertex into the queue. Okay, or initially one step you can put this step. So just enter the start vertex into the queue. So B. Okay, so I have entered this or insert this. Now now we will repeat the process. We will repeat the process. We will just take one element out from this queue, and that will come. We will mark this as a visited. Okay, uh, and after that we will check what are the unvisited vertex, adjacent vertex are available for this B. Okay, so we have this A, C, and D and E. So these are all unvisited initially. So initial setup, what you can do, you can just set all the vertex A, B, C, D, E, F as a unvisited. Okay, you can mark like as a 0, 0, 0 for all, or you can just give any like dictionary true or false you can put. But once you are just fetching the vertex, so implementation may be different, little bit different also, but I am just telling the concept. So once we are removing one vertex from the queue, we will check all the unvisited adjacent of this, and we will insert into the queue. We will completely insert this set into the queue. Okay, so then A, C, D, E, any order you can traverse. Okay, so this set I have insert into the queue. So now this is already out. Next time you can see to checking the next node, what node will come out. So only
A.
the all
Sir, one
neighbors.
thing.
Huh.
Here, the B will come out after we have inserted all the neighbors, right?
Yes.
Because we have already covered the all the adjacency, means like all the neighbors that are possible. For B, actually we traverse till all the adjacent, and then now we will traverse on the adjacent of B, like A, C, D,
Yes.
and
So
whatever.
this is the first step actually you can put.
Mhm.
Starting node always insert into the queue as a initial setup.
Okay.
Okay. After that, repeat the process. Always remove one of the vertex from the queue and insert all the unvisited adjacent into the queue. This is the repeated process.
Okay.
Okay. Once you are removing the vertex from the queue, mark as visited. Okay, so here I am doing this. So I have removed the B, mark as visited, so that is mark as visited. Now I'll check what are the unvisited vertex. So we have this maintaining with this information which vertex are visited or which are not visited. Okay, so when we are looking the adjacent, we will check that is visited or not in our record. So we will only take the vertex which are not visited, and we will insert that all the adjacent into the queue. So you will always get the order that adjacent level by this way. Okay, so because all the adjacent are put it insert into the queue, so only those will come first. Okay, so in this way, so B is now traverse. So after B, you will see that A. Okay, so this A will be come out. So A you will remove. So now A will mark as a visited. Okay, so now you are looking for the adjacent of A. So in this way, one second. In this way, multiple entry are possible. So that I'll also explain the another way to this. So in this way, A we are looking. So B and C. B is already visited, but C is still not marked as a visited. So C will again insert. Okay. So B and C again will insert. But that will not affect your traversal, because once we will fetch this information, next time we will fetch this information, this will not affect our traversal or anything. Okay, so this is the one way you can solve this. Another way is when you are like pushing into the queue, at the time you can mark that are visited, all are visited. Okay, so in this way you can also solve this. Another way which I'm just trying to explain, so that is okay, when you are inserting into the queue, at the time mark as visited. So in this way you will actually save the repetition insertion of the queue. So suppose B you are inserting into the queue, mark visited first. Okay, and when you are removing that from the queue, and what are the adjacent of that, just mark as visited first and insert into the queue. So this is the another way. In this way, that another so that when you will get the same vertex, adjacent vertex next time, so that is already marked, so you will not insert again. So but both way you will actually follow this BFS concept. So I hope this is clear. Let me just go to the step wise. So suppose, okay, so let me clear this and again explain. Oh, completely. One second. Again, let second approach, let me explain. I think that is given in the code. So I'm maintaining one queue. Okay, empty queue. So now this time, first I'm starting from this as a start. Okay, so before inserting into the queue, I will mark as a visited. So that is initially all are unvisited. So B. Okay, so I will mark as a visited and then insert into queue. Now we will repeat the process, same process. Okay, now I will just take out this from the queue B. I will check all the unvisited vertex. Okay, so all the unvisited vertex are A, that C and D and E. And at the time of insertion, same time, because all these are unvisited, so I will visit now. Okay, I'll just insert that into queue and mark at the same time. So mark this as true. Okay, A, and then C, then D, and then E. Okay, all marked. So now so this is already out. A, C, D, E. Now what vertex will come out first? So only A. So this time I will check A, B, and C are the adjacent. So B and C both are already marked, so this will not insert again. So okay, so once I'm taking A from the queue, nothing is inserting, okay, because all the adjacent are visited. But after that I will take out C. So C have B and G and A. So AB is already marked in this as a visited, but G is not marked yet. Okay. So D, E, F, and G. G is not marked yet. So we will just get one G from the C, and so that will insert, but we will mark also at the time of insert. Okay. So that will insert here, but at the time. Now from check from D. So from D you have E, B, G, F. E, B, G is already marked, but F is still not marked. So that only F will come. So we will mark here and push here or insert here. So F. Now each vertex. So if you will remove D, D have already done E. So E you have only the vertex which are all visited. Okay, so nothing will happen. Then H. Okay, this H, then nothing is happen, then F. So we will repeat this process until our queue become empty. So at the last, once our queue is become empty, we will stop the process. At that time, our each vertex are now visited marked, and you will see the order as per the BFS rule.
Sir, these
Sir,
all are.
Okay. Huh?
sir, why should we wait until all the this one is traversed? Because when we know that all are visited already, we can stop the traversing, right?
But we have to like make some logic here for here. Otherwise, you have to write something where you have to check every time all the visited or not to stop this. Okay, you can do, but you have to write some logic for that.
Okay, okay.
Or
So,
the simple logic is once your queue become empty, that means your task is done.
okay.
Okay, because we are not visiting the vertex which are already visited. So that means once your all visited vertex are visited, nothing will be insert again. So that stop will finish. Okay, after next iterations. So this is the concept of BFS to traverse the algorithms. Okay, so as I said that this generate a like a tree order. This generate like a one tree traversal. So let me so BFS, this algorithm is given. You can just show this structure also slides. So where what information we maintain. So we maintain one visited dictionary or something, or queue we maintain. Okay, so step by step how we start. So 0 we are starting as inside the queue. So now you can see from 0, 1 and 2 are the adjacent. So we mark 1 and 2 are the visited and inserted into the queue. Okay, after removing the 0. So next level we will see the 1. So now from 1, 3 and 4 are visited. So 3 and 4 are inserted and mark as 2. And the next level you will see only elements are removing because all become true. So only this part will be done and your process is stopped. So this is the traversal order, and same things we have done in the implementation. So if you relate this concept to the implement, so this implementation is doing the same things. And now if you understand the concept, try to implement by your own, because now you know the logic, what are the data structure you required here to maintain this. Now you can try with this your own instead of understanding the other implementations. So Q we are just taking as a data structure, okay, to maintain this. So this implementation you have already seen in the previous week, but this is the main part. So you can see we are maintaining the visited dictionary, this part. Okay, now in next part we have initially all set up false, and we created one queue. Okay, because we have the queue class, so we have created a object of class. Now initially we have set this visited start vertex equal to true. Okay, we have marked start vertex as a true and insert into the queue. Now repeat the process. So just repeat the same process while loop. Okay, so now we will repeat this process until our queue is not empty. So every time we will just take one element out from this queue, current vertex, and we will check adjacent vertex of the current vertex which are not visited. Okay, and we will mark that as a visited and insert into the queue. So we are taking one element from the queue, checking all the adjacents, and which elements are not visited, we will mark as a visited and insert into the queue. So this is the loop only running. And once this loop will stop, we will return the visited dictionary. Okay. So this is our input. So you can see adjacency list we are passing. So this is the graph information and calling the function. And after that, this is giving to this information, means all the vertex are visited. So this is code execution. I think it's not loading. Maybe it will load. So this is just like a Python tutor implementation, and this is with the adjacency matrix. Okay, so you have seen that how we are getting the adjacency information from this adjacency list data. So you can see this part. Okay, so here this information is just like a constant operation. We are just only passing the vertex as a key. We are getting all the adjacent data to check. But the same things we have to do with the adjacency matrix by a complete linear loop. Okay, so we have maintained this function to do this for task separately. Okay, our remaining codes are same, but only this part is costly. So if you see the remaining code BFS, so all the codes are same. So we have just marked as a, you can see same false, then queue created, then initial vertex visited, then inserted into the queue, when the same while loop remove the front of the queue, and then now we are calling this function to get this adjacent information, and this is the function which we have declared. So that function is actually traversing each column, and this is just like a order of week operation to get this or adjacent information. Okay, and then we are doing the same things.
Sir, can you show the neighbors function that was defined?
So that neighbors function is this. Okay, so we are passing the complete matrix and I, which we are looking the adjacent nodes for I. Okay, now we are just created a one list that will collect all the neighbors, but to get all the neighbors we have to traverse this all columns. Okay, so we are just j in
Check
the
whether
false,
the
value
there
is
is a
one or
node.
not.
It just checks
Okay,
na,
so but we, yeah,
nodes
yes,
exist
yes.
or not. There are there is a
So we are
connection.
just checking that in the matrix this value is equal to 1 or not. And
So
that j value we are appending as a neighbor. Okay, so for each columns we have to do this check.
this is very costly, right?
So this is order simply linear, actually order of b
Order of
operation.
n or v, whatever, yes.
So because of that, this is costly with adjacency matrix.
And in earlier
Otherwise,
one,
the implement
adjacency list.
that is simply that is just a constant operation.
Because
Okay, that is
individually
simply,
we can do, and neighbors function will change to a mat comma v, and it will just check for the keys, right?
yeah, that will run completely. But in the adjacency list, we are directly calling the key and getting the value. Okay,
I
in
tried
constant
creating it myself. It's like this neighbors, though my implementation was little different. It was mostly checking the value adjacent to it and then doing it. But yeah, it's like rest of the things were same, but this neighbor function, as it was not given in the lecture and I didn't went to this particular notes, so that's why I created my one.
Okay. Yeah, because of that, we have initially explained all these things. So how this neighbors actually calculated. So because same implementation we have done.
No, this is a simple implementation actually. I was doing a complex one.
Okay. Okay, so this is the thing. So so some, now this is the traverse main part. Some additional information we can get this from this the same BFS. So like find parent of each vertex using BFS. So once we actually perform the BFS, so I think any graph is given. So suppose this graph. So when we traverse the BFS, actually it generates the tree, as I explained earlier. So it generates the tree, and that is also represent the shortest path in the terms of number of edges in the root to leaf path. Okay, so suppose if I just start exploring from 0. So you can see we will get 0 first. What are the adjacent of this is just like if 1 will be traversed, then 2 will be traversed in the next level. So and after that 1 we will see 3 and 4. Okay, so 3 and 4 we get this because this is traversing neighbor wise. So this will not get the uh, like lengthy path to get the visited node. So if you are starting 0, so if you see that this tree, so you will always get a one path from root to each leaf. Okay, so that is the shortest path in the terms of number of edge in this path. So 0 to 4 you will see. So this 0 to 4 means 0 to 1, then 4. This is the one path. Okay, and this is the shortest path in the terms of minimum number of edge in the path or minimum number of vertex in the path. Okay, so both we can see. Otherwise 0 to 4 you can also traverse in multiple ways. So like 0 you can go here, then you go here, then here, then here, like. But this is the this is not a shortest path. Okay, so in this way. And here if we are looking, if you're traversing the vertex neighbors wise, so you will always get this type of tree, and where only the one shortest path is possible from any vertex to any other vertex. So this generate a shortest path from the starting node to each another vertex. In the terms of, here I am just explaining that this is the shortest path in the terms of minimum number of edge or minimum number of vertex in the path, in the terms. Okay, so this is also questions can be asked, okay, in the real life problems. If we are looking the, suppose if we have the structure of railway stations, and we are looking the shortest path in the terms of number of stops in between. So that in this way, here distance we are not looking, we are looking the minimum number of stops in between that any starting node and to another node. So then we can apply this type of BFS algorithm, and that will provide a path with the minimum number of vertex in between or minimum number of edge in between. So here 2 edge are there or 3 vertex are there, including start and last. So this is one type of application of this BFS traversal, and we get this information. But to get this path, actually we are traversing, we are applying the BFS, but we are not maintaining the parent node actually. So here you can see we are getting 0 traverse first, so we will only get this order 0 1 2 3 4 like this, but we are not maintaining any parent information, means at the 4 where we are coming from actually. So this information we are not maintaining. So if you maintain this information for each vertex, so means when you are visiting 0, so this is the starting vertex, but when you are traversing the adjacent of this 0, at that time just maintaining that the parent of 1 is 0, parent of 2 is 0. This information additionally you can store at the time of when you are traversing each adjacent levels. Okay, so when you are traversing like 1 and 2, means this 1 and 2 are the adjacent of 0, because of that you are traversing these. So just mark as a parent 0 for both. So by this information, if you maintain this information in your logic, so that what are the 3 and 4 parents, that is 1. In this way you can also get the path information. So how you can get the path? Suppose if you're looking the path from 0 to 4, so start with the destination. So what are the parent of this 4? So parent of 4, this is 1. Okay, 1. Then again check what is the parent of 1. So parent of 1 is 0. So repeat this process until you will reach at the starting vertex. So by this information, just you can store this information as a parent node, and then you can get the path also by this information. So same concept we can use in the Week-5 shortest path algorithm. So if you maintain the path of each node, sorry, parent of each node, then you can also get the complete path information also. Okay, so this is the one additional things you can do with this code. So other implementation are just like some modification or some additional things. So find parent of each vertex. Okay, so this is the part. So what we have done at the time of when we are storing this, we are doing this process. Okay, we are marking this vertex is visited. At that same time, we will also send the parent value. So initially parent value we have assigned as a -1. Only the start vertex will contain the -1. Otherwise, all the remaining vertex will contain the parent value by this line. Then you can get this parent dictionary also. And by this dictionary, you can achieve the complete path by just repeat the reverse process, destination to next, previous destination, that like this. Now find label number. So as I said that we have this adjacency list. Okay, so not adjacency list. We are traversing by the BFS adjacent label wise. Okay, so if you're generating the source vertex at like this one, okay, like this 0. What are the next adjacents are coming? This. At that time, also assign the label. So you can assign the label with this as a 0. At the next time when you're traversing all the adjacent of this, just increment the previous label to y1, and that is called as a 1. So each node at this level will consider as a label 1. Okay. So next label will consider as a label 2. So by this information, you can return the length of the shortest path by directly by this label information. Okay, so you can check what is the label of this vertex. So that is 1. So means length of this path is 1 in the terms of edge. Okay, so that label information you can also modify, get this by some modification. So so this is one additional things, label of the vertices. So in the additional code, so label each vertex is initially -1, parent of each vertex is -1. So we have added some more additional things, and this label we are adding here. Okay, so we have added one line, and then we have modified this. So all the implementation are same BFS, but we are just modifying little bit to get more information. Okay, so now this is the BFS, and the same things. Okay, that will come under the application of both. Okay, so now this is BFS. Now comes to the DFS part. So DFS, I think it's become more lengthy. So DFS, as per the name, the depth first search algorithm is used to traverse a graph or a tree in the depth first manner. So depth means we will just start with any vertex. After that, we will traverse the one of the adjacent of that. After that, we will not check the remaining vertex here this time. We will check the next adjacent of that vertex. Okay, so we will just traverse, complete the depth first until we can visit it at the last. Then we will reverse back and we will check the another possible depth. So this is the concept of DFS, and let's show you the example. Okay, so just start with the same example, 3 examples. So like you have this A, okay, suppose if this is a graph, I am just saying, okay, so this is a graph, not a tree. So suppose if we start, or let me connect this like this, so you can connect, so this becomes a complete graph. Suppose if I am traversing from A, okay, this is the starting vertex. Here I'll check what are the adjacent of this A. Okay, now B, C, D are the adjacent of this. So B, C, D are the adjacent of this. We will pick one of the adjacent. So like if I'm picking B, so means A, I'm just moving to B. Now once I am just traversing to B, I will check the next adjacent of this B. Means we will complete the depth first where I can reach from this path depth. Okay, so B, again we will check what are the adjacent of B. So B have the adjacent of B is, so that is like E and F. Okay, so we will just move to one of the adjacent, so that means E, and then we will again check the same thing. So we will just suppose we will move to G. Now there is no next adjacent point after this. Okay, G. So we will reverse back to previous vertex, and we will check what are the another adjacent remaining for this. So okay, so for E we have G and H. Okay, so for E we have G and H. So we have moved to G, completed the G this path, and we will revert back to E, and we will check the another path. So that is H. Now from H, where I can move, so I can move E and I both. Okay, so we will select any one of them. So suppose I'll check F. From F I can move this C, B I have already done. I can move. Okay, so I can move in any of the adjacent. So suppose I am moving I. Now from I you can see H is visited, F is visited. So I will revert back to this and will check what are the remaining adjacent from this F. So that is C. Okay, so that is C. Now from C you can see we can also move to D. So that D will also come. So now from D nothing is pending. So you will revert back to C, nothing is pending. Then F, then H, E, B, A. So this depth first search traversal you are getting. Again, you will get a tree, but this time you are completing first one depth to reach at the last point, then revert back to check the another depth. So this you are getting from the DFS order. Okay.
Sir, when you're reversing
So
back, sir, once you reach G, you have to go back to C and then start the depth, right? Because you first started with A
no, from
and then
From G we will not revert back because where from we are coming from G, E, na?
E, E,
So we will revert back only to the previous one
or previous one.
position.
Okay. Hmm.
And from E we will check if any another path is possible from this, because we have the another path this side. We
Okay,
have not
okay, okay.
visited yet. Okay. Then H. From H we have two possible adjacent. Okay. So E, F and I. So we can traverse any one of them. Suppose we are traversing F. Then from F we can again C and I. We have two possibility which are not visited. So we can select any of the one. Suppose I. But after I there's nothing we can traverse, all are the visited. So we will revert back to F. Then F to C we have not visited. So this path we will move. So that we are moving here. And from C we have D which is not visited. So D. Once we will reach at the D, now no adjacents which are remaining, so which are not visited yet. Okay, so this is now completed. So when we will reverse back, so nothing will actually remains unvisited. So you have to reverse back till A, but you will not get any vertex which is not visited yet. So this is the DFS traversal. Okay, and this we can achieve through the stack. So this is also very important question. So what are the data structure we use for the BFS and what are the data structure we use for the DFS? So BFS we use the queue, DFS we use the stack. You can use like stack external stacks in your code, or you can achieve the stack implementation through the recursive code. For recursion is also use the stack concept internally. Okay, so both way you can achieve this this traversal, DFS traversal. So here if you see this, just you can see these steps. So these steps are also doing the same things and working visualization. So as I mentioned that here also, so we will maintain one stack and visited marks. Okay, so here we will just traverse one of the visited. Okay, so stack we are removing two and we are inserting one of the adjacent vertex, any one of the adjacent vertex. So here we will just check the adjacent, but one of the vertex we will insert into the stack. Okay, so now we have moved to 1, so that 1 after from the 1 we can move to 3 and 4. So because of that, after removing this 1, so we have inserted 4 and 3. Yeah, all adjacent actually we will insert into the stack. So let me show you that. So when we have just traversed 0, so actually in the stack I'm just representing like this. So this 0 is the top of the stack. So every time we will remove the stack one of the from the top. Okay, and we will insert all the adjacent into the stack in this way. So when we are removing 0, so this 1 and 2 both will come into the stack. Okay, like 1 and 2. So means you have traversed from 0 to what, like okay, so after visiting 0. Okay, so after that which node you are picking. So like suppose if you are picking 2, so this is the next visited vertex. Okay, so when you're removing 2, what are the adjacent of 2, 3 and 4? So next level after removing 2, you will get a 1 in the previous, and 3 and 4 will come next. And then you will remove 4, so 4 will come into the next depth, and after 4 you are getting 1 and 2 and 3, but all are this time here you have to still you have to post if it is already in the stack. Okay, so because this steps we have to follow here. But any vertex which is not visited, visited, already visited, that we will not insert again. But any vertex which is not visited and still already in the stack, then still you have to insert into push into the stack. Doesn't matter it is already there or not. So when you are removing 4, so 4 when you are removing, so 3 2 1, so 3 2 1 you are getting, but 2 is marked as visited, but 3 and 2 is again coming, so you have to insert again. So 3 and like 2. Okay, so in this way 4, then you will repeat, 2 is also marked, 3 and 1. So 1 you will fetch, so 1 will come from 1, you have like a 0 3 4, so 0 3 4, 3 and 4 is already done, not done. So 3 and 4, 4 is already done, so 3, what I have removed 1, so 1 0 4 and 3, so 0 is already done, 4 is already 3, only 3 will come. So after removing this one, so 3 will insert again, then you will fetch 3. So you can see all are now visited, so 3 will be removed, then again next 3 will be removed, next 3 will be removed, and 1 is also will be removed. Okay, without changing anything, so you will get this order, DFS. So in this way, this is the implementation of stack. Okay, so we are repeating this process. So you can see 2 is already there in the stack. Still, again we have inserted. So 4 is repeated 3 times in this. So last it was 2 home. So we will only not post the node which is visited, but if any node which is unvisited, we will always post. Doesn't matter that is already in the stack or not. This is the step here. So now the implementation, if you see, so we are using externally stack, okay, in the same way. But now this is the DFS algorithm. You can see the steps. So what we are doing, we are maintaining the visited vertex, initially all the false. We have created the object of a stack. Initially start vertex post into the stack at the top. After that we are repeating this loop, the same things until our stack is not empty. Then we will just pop one of the element from the stacks as a current vertex, and we will just mark, we will check if visited current vertex is equal to false. So as I said, implementation may be a little bit different, but the concept will remain the same. So in these steps, visited current vertex equal to false. Okay, so we will check the current visited vertex. This we are looking as a adjacent visited current. Okay, so what vertex we are removing from the current vertex? First we are checking if it is already visited or not. If it is not visited, then we will mark as a visited, and we will just check all the adjacent vertex of that. If that not visited, we will post into the stack. So same things we are doing, but some part where we are just changing the things, and the data structure we are only changing, and you will achieve a DFS by this. The information you are getting the same. Okay, so we are just getting the same visited information of the vertex by this also. That means purpose is same. Okay, true like this. And now recursive, this is little bit confusing to understand, but this is also doing the same things recursively. Okay, this is the recursive code. So here once we are actually, if you see this code, so DFS, and then so visited v equal to true we are marking, then after that adjacent vertex we are looking for this adjacency list. If it is not visited, then we will so here we are also maintaining the parent, so this is additional task thing, but we are just calling the same DFS list algorithm, which is the same on the child node, that one of the adjacent vertex. So this is just following the recursive call onto the same child vertex. Okay, and this will repeat the process. So internally this is handling the stack things. So but imagination, this is little bit difficult to understand, but if you follow the steps and you maintain all the steps, you will get the same working. Okay, so if you are comfortable with the recursion, so you can also, I think, imagination this. But this is the same things. Now this is just like a different version of this, so you can also maintain this visited parent as a globally variable, so then you can do that same things. So this is just like additional things. Okay, but you should know the concept of PFS and DFS. So implement adjacency matrix. So same things for adjacency matrix, you have to get this neighbor information addition from the neighbor function like this. But adjacency list, we are getting this and the constant time. So same global information, this is a little bit modification. Yeah, application of BFS DFS. So here one of the very important application is find connected component. Okay, suppose if your graph is disconnected, like A, this is connected B, and then it's C, D, A, F, like this. Okay, suppose this is the one graph you have, and you are applying the BFS on this algorithms. Okay, this vertex. So what value you will get? So you may get this information that your graph is connected or not, because if you apply the BFS on this A vertex, you can only traverse this A to B, then B to C. Okay, then this is not reachable. So you will not reachable to another part of this. So you can get this information that this is the disconnected graph, because all vertex are not reachable from the A. But you can also get this information how many connected components are there. So you can run a loop, first apply you have the set of all vertex. Okay, so A, B, C, D, E, F. So what you can do, you can apply a BFS on suppose this vertex, and you apply it. Okay, so how many vertex will be visited from when you applied the BFS on this vertex? So this A will be marked, B will be marked, C will be marked. So now you will check that any other vertex which are not visited yet. Yes, so this set is not visited yet. So again, you will apply the BFS of another part which is not visited on D, suppose. Okay, so once you visited applied BFS first times, you can mark as a this is a first component. But when you applied the DFS on the remaining parts, so if suppose if you apply BFS here, so D will be marked, E will be marked, F will be marked. Okay, in this process. This is just like a second component. So in this way, you can repeat the same BFS algorithm until all the vertex are not visited. Okay, so this process we will do to get the number of components. So same things you can do with the DFS as well as the BFS. Okay, so this is the one application, and this code information is given in the code. Okay, so find connected component. You can see so this is, you can see BFS, we are calling this algorithm now. This is the additional algorithm, but the main component algorithm is this. So from this algorithm, we are calling that BFS algorithm to one vertex, and we are marking that what are the number of vertex which are visited from that one call. Okay, so this is the implementation of BFS or entities which we have already seen, and this is the additional part to get the component information. So this is just like the same things. We are just applying the BFS until we will get the all nodes visited. So that number of times. So you can see this implementation. All the comments are given in this, and okay, this pre and post numbering using DFS. This is the last vertex. Okay. Okay. So pre and post numbering is also one concept of this DFS. So when we traverse the DFS algorithms, at the time when we are actually calling the function new actually adjacent matrix, we assign the numbering actually. Okay, at that time. So suppose we are calling this DFS at the first time from this one vertex. So we will assign a pre-numbering and post-numbering this value. So how this will be assigned? So let me see that value is given or not. Okay. So how this is assigned actually? Each vertex have pre-numbering and post-numbering. So like pre and post. Okay, each vertex this information. So pre, when we are actually start with one vertex, so pre value we will assign for this 0. Okay, now we have moved to this. So pre value we will assign for okay, so where from we are starting with this example. So we are starting with 0. Okay. Minus 1. Minus 1. Okay. So this is like this. We are starting from this vertex. Starting from this vertex. So pre-numbering for this is 0. Suppose if I traverse this part first, the DFS, so 0 to 1. So pre value for this will become 1. But after that, we don't have any another non-visited vertex, okay, from the 1. So when we will return back, actually at that time we increase the post numbering. Okay, when we are calling, when we are moving from first time to another unvisited vertex, at the time we increment the pre numbering, but when we return back, at that time we increment the post numbering. So pre value, so like pre for this is initially 0, and now we are moving from 0 to 1, so that is become pre for this is 1. But now we are returning back because nothing is remaining from here. So we're returning back. At that time we will increment the post value. Okay, so post will become from the 1 to 2 here, like this. Okay, now we come back here, and from this 0 we can again move to another side. Okay, so like 0 to 4 we can move, so that pre numbering for this 4 is become like pre, this is 3. From 4 we can move either 8 or 9. Suppose I am moving to 8, so pre for 8 is become 4, and from here, like suppose if I am moving, so pre of become 5. Okay, but from 5 now all are visited, so I will return back, so that post I will assign here. So post will become 6, then revert back. Now from 8 I will revert back, so post will assign for this is 7. Now I will revert back here, so that, so from here, so post will become 8. Now revert back to this 0, so that will become post value as a 9, because now it is completed. All this will remain minus 1. Okay, because this is totally separate, disconnected. So this information we are getting by the code. So, and with the help of this pre and post numbering, you can identify the edge type. Okay, so that is covered in this lecture. So with this range of this, actually you can get this information that what type of edge is this actually. So let that formula, let me discuss. So
Sir, I have a question for this. Uh, the pre for 4 is supposed to be 0, right?
no, pre actually we start from the first vertex where we are starting.
Okay.
When we traverse first time, that we increment the pre. Okay, and when we return back, then we increment the post. Okay,
Oh,
but
this
that
is there
increment
incrementation happening.
that increment happened from the previous value only. Okay, so we started from the 0. You can see we started from this 0 vertex as a starting node. So pre was 0. From 0 we can move to 1. As we are applying the DFS here. Okay, so we are applying the DFS, and from 0 we can move 1. So we will increment the 1 from the previous value. Okay, so that is now become 0 plus 1 1. But now from 1 there is no unvisited vertex from this. Okay, so we will return back. Once we return back, at that time we increment the post value, but increment happen continuously. Okay, so that 1 plus 1 2, this will become 2
So can you
for post.
explain this pre and post numbering again?
Okay, so let me open the slide. I think the slide will see for that. One second. Just give me some time. In the slide. PTS. Number of this one. Okay, so see this where the professor have discussed this numbering. So let me take that example to explain. Well, oh, this is also there. Okay. So see this example. Okay, so here let me start this example. So how the numbering is actually calculated for this. So we are starting from 0. Okay, we are applying the DFS here. Okay, so from 0 we can move 1 to 5 this vertex. This is the directed graph. So we will just take this as a pre-value for this is I'm just writing pre-value as a 0 here. Okay, starting value. But after that we will suppose we traverse the value numerically first. Okay, so after that suppose 0 to 1 we are moving, so pre of this will become uh, so this will become like this. Okay, so 0 we are moving, this is the first vertex, and 0 I am assigning here. Okay, pre-value. From 0 I can move 1, so pre-value for this will become 0 plus 1 1. Okay, from 1 where I can move, we can move 4, so I can move to 4. So pre-value for 4 will become 2. Okay, now from 4 I can move to 5 and 7. So let me move to 5. So that is pre-value is I am incrementing only pre-value now, 5. From 5 I can move to 7. So 7 is just like this. So 7 pre-value is 4. Okay, now from 7 can you move anywhere else? No, there is no outgoing edge. So at the time, once there is no possibility to move again, and we are returning back. Okay, this is just like a previous. We are just returning back to the previous call. So we are returning back. At that time, we will increment the post things here. Okay, so this was the left side. Left side, all the number are considered as a pre, but right side considered as a post value. Okay, so this is now become a 5. This is a post numbering. Okay, now we are returning back to 5, where we can move to 5. So we can move to 1, but 1 is already traversed. Okay, so nothing we have to move from 5 also. So 6 is the post numbering for 5. Now move back to 4. So from 4 is anything is remaining unvisited? No. Okay, this is now 7 post numbering. Okay,
6 is there.
so hmm?
6, 4 to 6.
No, 6 is already there, na?
No.
5, 6. So we
No,
are
no.
incrementing
In
from
the
the
graph,
previous number.
in the graph 4 is pointing to 6.
Oh yeah, correct. Yeah. So that is not correct. So 4 to 6 is there. Yeah, correct. So 4 to 6 is there. So 6 is there. So pre-numbering will increment. So 6 plus 1 pre-numbering is 7. Okay. Now 6 is anything else? No. Now post number will increment when we will revert back from this. So that is 8. Okay. Now we will come back to 4. Now nothing is remaining. So this will become a 9 post numbering. And when we will return back to 1, nothing is remaining. So 10. Okay, now this is post numbering. Okay, and we are moving to 0 now, but from 0 another path is possible, so that is 2. So that pre-numbering is become 11, and 2 and 2 to 3, so that is 3, that is 12, and 3 to 6 is already done, so nothing is remaining. So now post numbering increment revert back, so that is 13, and from 2 that is 14, and revert back to this, that is 15. So this is the pre and post numbering how we are doing at the time of DFS traversal. Okay, so let's see we are getting the same or not. So you can see this is the numbering which professor have calculated. So I think this is same. 4 5 3 6, yeah, this is the same. So I think this is clear to understand by the color. So we have done the same things here. So this purple color is pre-numbering and this green color is post-numbering. Now after getting this pre-numbering and post-numbering, we can identify that what type of edge is this actually by with the help of this pre and post numbering. So each edge we can identify. This is a for original graph also you can identify that what type of this edge is there. Okay, so let's just make all the edges in this graph with this tree. So you can see we have this. So now we will just add all the edges which is not part of this tree from the graph. Okay, so you can see from graph. So 0 to 1 you have already there this one, but 0 to 5 you also have, but that is not a part of this tree, but we are making by this green line. Okay, so we are just now representing all the edge. Okay, which is already there in the graph. So this is the original graph. Okay, we are getting the sum of the edge in the tree, but now we will also add the edge which is in the original graph but not in the tree. So that finally we will get all these edges. Okay, so you can see this this is now complete things. Now the here color combination is also there and you can identify that. So we have the three type of edge, or we have the four type means. So this is the final version when we included all the edges. Okay, including from the original graph. So now here forward edge, back edge and cross edge. So forward edge and oblique tree edge, and no tree is as the separate. Okay, so tree edge which are coming in the traversal tree. So that black which is representing, that is a tree edge. Okay, forward edge which is coming from the root to leaf side. Okay, so this green edge which are coming edges, that is called as a like forward edge. Okay, that is coming from the top node to like bottom node sides. Back edge is just like a reverse edge, leaf to bottoms, that lower level to higher level side. That is called as a back edge. Cross edge is just like a from another branch to another branch. Okay, so like this is the different branch and this is the different branch, and this edge is just like a crossing the different branch. So this is called as a cross edge. But how we can identify it? With the help of this numbering actually. So in the original graph, if you will see, so what type of edge is this actually? Okay, so that we can identify with the help of this pre and post numbering, this information. So that you can see there are the condition for each here. So for tree edge and forward edge, this, if we are looking for u comma v edge, okay, any edge you can take, what are the u value and what are the v value, and just check if the pre of u and post of u, this range contains the pre of v and post of v, then that edge is called as a tree edge or forward edge. So how we can check this? So let's I want to check this 1 to 4. Okay, so 1 to 4, this edge in the graph. So this edge. Okay, this is a tree edge, back edge and like a cross edge. So just consider that this is a u and this is a v. So according to this definition, pre-u and post-u, what is the value of pre and post for this? So pre is 1, okay, and post is 10. Okay, so 10. So this is the range. If this range contain the same, check for the v. So what is the pre value for 4? That is 2, and post value is 9. So see, this range is coming in between this range. Okay, so 2 comma 9, this range is coming in between this range 1 and 10. Okay, so interval pre of u comma post of u contains this value. So if this is true, this edge is actually called as a 1 4 edge is called as a tree edge or forward edge. Okay, Now the definition, so this is the main application basically. If you want to check the graph as cycle, so for this graph has a cycle, so you can just check if graph has any back edge, means graph has cycle. So how we can check the back edge? So we can check if interval of pre-v and post-v contain pre-u and post-u. So this is the thing we have to check. So suppose any back edge like 3 to 0. So 3 to 0 is the this edge in the original graph. We are just looking that this edge is a back edge or not. So what is the pre value? So this 3 to 0. So this is u and this is v. So here just check pre and post value for 0. So 0 and 15. So, okay, so 0 and 15. And 3, 12 and 13. So 12, 13. So here see, if pre of v, post of v, this one contains the interval of this. So 12 and 13, this is coming in between in this range, 0 to 15. So if this is true, means 3 to 0 is a back edge. Okay. So, and this also represent graph has a cycle. If any graph has any back edge, so means graph is a cycle. Cross edge, if both range are distinct, okay, separate. Suppose cross edge like this 6 and 7. So 6 to 7, if you see, so what are the pre-range and post for 6, 7, 8, okay, and for 7, 4, 5. So both range are distinct, okay, not coming in between any, okay, 7 and 8 and 4 and 5. So this edge is called as a cross edge.
Okay.
So after,
If, for the interval 1 to 10, there is a 2 to 9 interval, so it is forward edge. When 12, 13 is coming in 0, 15, that is a back edge. When 7, 8 and 4, 5 are there is no common in those, then it is a cross edge.
yes, cross edge.
Okay.
Yeah. So we can check this by this pre and post numbering. Do not check this coloring in the tree. Okay. So we get this information pre and post numbering for each vertex. After that, in original graph, you can separate all the edges. What are the type of that edge? Actually, with the help of this pre and post numbering formula. This. Okay. So you can identify that which edge in the original graph is a tree edge or forward edge or back edge or cross edge. Okay. If your graph contains a back edge, by just checking this, okay, just check that if any interval pre v or post v contain the range of this pre and post u. So that is the back edge. By this formula, you can just identify that the category of edges. Okay. So this is one application, and back edge is directly represent the cycle in graph. So this is also one application of this. So this is the purpose, or some other purpose is also there, but that is not covered in the course. So this is the one of the important purpose. You can figure out the type of edge. Okay, so this is the pre and post numbering. So implementation are also doing the same things. So if you see the quickly implementation, so and the recursive steps we are implementing the post. So implementation, you can see we are just applying the DFS, okay, pre-post DFS algorithm. But at the time, you can see this post V, okay. So pre-V, we are just taking this count. That is one pre-post DFS, okay. Yeah, so we are taking this one global variable count, okay, every time, because we are just incrementing from the previous value, either pre or that post. So because of that, we are maintaining one count variable. So when we are coming to any vertex, we are incrementing this pre-v, okay, we are assigning this pre-v for that value. But then at the time of recursive steps, okay, this is the recursive part. Once the recursive call will complete, we will revert back and we will follow these steps. So at that time, we are assigning a post value. So that is the recursive way when we are returning back. So at the time, post value will be assigned. So you will get a pre and post numbering like this for each vertex. And after that, you can figure out. So this classification is given. So for tree edge and forward edge, check this condition. For back edge, check this. and for process check this. So just remember this interval formula for this, okay,
So in
and how pre and
OPP,
post
we
number.
have to do all this implementation.
No, so not required all the implementation, but yeah, main algorithms BFS and DFS you should know.
Okay.
Okay, other algorithms are just like some additional version of that, but main conceptual like algorithm are BFS and DFS
And
that
I
you should know.
mean, this deep kind of questions will get in OP, I'm asking.
No. That OPP, this type of question is not asked, but yeah, for exam, quiz,
Uh,
that type of
okay,
conceptual
okay.
question will ask. Okay. So now this is the one remaining part, deck. I'm not sure how much energy you have to get this. Okay. So let's try this. Watch the lecture. Okay, and maybe we will conduct the revision session for next week for the quiz, and you can ask this part, deck part. Okay. Just first see these notes also as well as see the lecture, okay, and then just see these notes. If you have any doubt in these, then you can ask in the next revision session. So Friday we will conduct the live coding, but next week we will conduct the revision session for the quiz one, so you can ask that. Okay, so because most of them are left now. Okay, is that fine? So I hope you can watch the lecture and you can come up the doubt, or you can ask this in the TA session. Okay, then
Okay.
yeah, we can close the session. Thank you, everyone. Bye.